folks, here we go, picking up right where we left off. I want to go straight into it. We're going to pick up from this problem we just did, particle in a one-dimensional box. And we're going to expand this to 2 and more dimensions, okay? So, in other words, we're going to start making this more physically realistic. So instead of our particle that can only move left and right in our 1D, we're going to now go to 2 dimensions, okay? And we still quite don't have a full 3-dimensional situation yet. Excuse me. So in other words, in this 2-dimensional problem, right, our particle is confined to this surface, okay? So it can move, back and forth in this dimension or back and forth in this dimension. So it's still confined to this little surface, but all the same, we've added 1 more dimension to make this a little more realistic. And we'll see right away, this is where this problem is going to blow up. This is where it really, really starts to get complicated. But we can do it, okay? So let's first establish what we know. Well, we know h psi equals e psi. Great. We know here we're still talking about v equals 0, okay? So my Hamiltonian is only kinetic energy, negative h bar squared over 2m times second derivative in psi. All right. But now, look, the way that we apply this to multiple dimensions here, okay? So this was 1D Hamiltonian. This now becomes our 2D Hamiltonian, okay? Where now, instead of having d dx squared, we have partial of x squared and partial of y squared to reflect those 2 different dimensions, okay? So, and there's another thing that we can do, another important technique called the separation of variables, okay? That's how we're going to do this problem. So in the separation of variables, we impose that our wave function, right, which is now a function of x and y, okay, right? We impose that it can be written as 2 separable wave functions. So this is 2 separable wave functions. So in other words, this function x of x is a wave function that only describes psi in the x dimension. And this function y of y is a wave function that only describes psi in the y dimension. Okay? So let's set this up, all right? So what I can do now, I want to establish this as the following, and recognizing in my partial derivatives here, okay, if I take the partial of psi of xy with respect to x, okay, right, then I know that now this function y becomes a constant, so I can take that out in front, right? It doesn't depend on the derivative of x, okay? And now I only need to worry about taking the second derivative of the x function, all right? Similarly, when I take the partial of psi xy with respect to y, I know that now this x function doesn't depend on that second derivative, so I can put that in front, okay? And my derivative in psi is only dependent on y. So this is what allows me to separate these variables, okay? And so now I'm going to make a substitution up here. See where I wrote, second derivative an x of psi xy, second derivative of y and psi xy. I can now replace those with these two separable solutions, okay? And that goes as follows. So we'll say substitute, all right? And so now that's going to be negative h bar squared over 2m times, and now look, we know the second derivative in x can be written as such, the y function times the second derivative of the x function. Great. And then now plus, here is the y term, and I can write that now in terms of this separable solution, okay, partial ny squared, right? And then now, of course, that's still all going to be equal to e psi, but now instead of writing it as e psi, I'm going to write it as e times x of x times y of y, okay? And so now to solve this, the method I like to use is called divide and conquer. That's my own little established method. Divide and conquer. So how are we gonna do it? Okay, well, I'm gonna do a couple steps at once, just so you see what I'm gonna do, all right? First, I'm gonna move all of my constants over to this side, the 2mh bar squared. I'm gonna move that over, okay? And so I'm gonna write that down directly. So I'm just gonna say that that is negative 2me divided by h bar squared, okay? Now, what am I going to do? Well, if I divide both sides by x of x and y of y, okay, so I'm going to divide this thing by that, which means I'm also going to divide this whole thing by that, okay? Then here's what I get. Well, so I notice now that this, the x of x and the y of y cancels, so I'm just left with negative 2me over h bar squared. And remember, that came from just pushing these constants over to that side, okay? But now, since I divided out those functions, what I recognize here is, for this function, the y is going to cancel. And for this function, the x is going to cancel. But I have to remember, I'm dividing both terms by xy, okay? So now what I'm going to get from that is, so the y is canceled, but now I have 1 over the x function. So that's going to be 1 over x of x, okay? And that's still going to be times the second derivative in x. I still have to deal with that, okay? And now I'm going to have the same thing over here on this term, where now the x and the x cancels, but I still have the 1 over y. So now that's 1 over y of y. And of course, now the second derivative of that function in y. And that all equals negative 2me over h bar squared. Okay? So now what I can also establish is the following. I can establish that my solution here for E, my eigenvalue, it's going to be a linear sum of the two solutions in x and y. All right. And so what I can also do because of that here, okay, I can now just separate these two things. So this is where I'm going to do my separation of variables technique, okay? Because I know if I just looked at the two separated situations, I know in the two separated situations, it's negative h bar squared over 2m times my second derivative in x, which equals ex and x. So I know that I can write that if I'm assuming here from the beginning that I was able to separate my dimensions, okay? Then I know I could establish this. And I know that I can also establish the same thing for the y dimension. That equals ey y of y. And I'm also establishing that each one of these individual eigenvalues for ex or ey is a linear sum of the total solution. Okay. And what I'm gonna do, so the separation that I made here, okay, what you'll notice, what I really did, I skipped a step and I didn't describe that, okay? In assuming that these are separable, okay, if I just ignored the y term, right? Look, when I multiply through the x over to that side and then reestablish the constants, I basically just reestablish each individual dimension, okay? So this allows me to show that they can be separated based on the properties of these derivatives, okay? So in other words, it's once again, when I'm taking the derivative in x, I don't care about the derivative in y. And when I'm taking the derivative in y, I don't care about the derivative in x, okay? And what's pretty cool about this, let me see what I got going on. Oh, I left myself more room here. So let's just, I'm gonna expand on that just really quick because I thought I was out of room, but it turns out I have a whole other slide here. So let's just make sure that that's established. Okay, second derivative in this function in x, dx squared. Okay. And that was plus 1 over y of y partial squared for the y term. And then now this equals, of course, negative 2m ex plus ey over h bar squared, which of course I can write as negative 2m ex over h bar squared plus negative 2m ey over h bar squared. And yes, so if I just ignore, if I take away the y value, okay, then I effectively get 1 over x of x. And I'm able to ignore these values again through the virtue of properties of these partial derivatives, that the dimensions that I've separated them, okay? And so now that's just negative 2m ex over h bar squared. And this actually, it's hard to see it. I know it's hard to recognize this. But now if I go back and rearrange this algebraically, let's just put it back together in the form that we all know and love. It's going to go as negative h bar squared over 2m. And so what I'm doing is I'm going to switch these two constants around, and you'll see in a second. I hope you'll see at least. Okay, dx squared. And now that equals ex just times the x and x. So again, all I did here was algebraic manipulation. And the result is it's just the same wave function we established for the one-dimensional situation. And then similarly, the same thing would manifest in the y dimension. dy squared equals ey y of y. And we've already solved this. I'll just back up to the very beginning, the particle in the box situation here. Right, we already solved this thing. Here it is, negative h bar squared over 2m, second derivative in psi, okay? And not only did we already solve this thing, but we solved it for the boundary conditions, and we also normalized it, okay? Let's see, here is our normalization, right? Root 2 over L. So what's pretty cool about this separation of variables problem and this divide and conquer is we've already solved and normalized these. So we can just use those solutions. So in other words, x of x is root 2 over, and I'll say Lx, because that's my dimension in x. And that's going to be sine of quantum number in sub x pi x divided by Lx, okay? Our solution for the y component will be the same, except for it'll be root 2 L of y times sine n of y pi times y over Ly, okay? And so I'll remind you that when we did separation of variables, right, we said psi of x, so the wave functions are multiplied, the energies are added. So now my psi of xy is just these two wave functions multiplied by each other, okay? And so that equals the following. So the root 2 cancels, and then you just have 2 square root Lx Ly, and then there's the sine nx pi x all over Lx, also times another sine, but this time it's ny pi y Ly. So these two quantum numbers, nx and ny, their quantum numbers are the same principal quantum number, but we're just establishing that we can change them in either dimension, the x or y dimension, because we did say these are separable, all right? And then now we also know because the energy solutions are additive, so I'll say E of xy ends up going as the following. It becomes n squared over Lx squared plus ny squared over Ly squared, and then we get this h squared over 8m. Okay? So what does all this stuff look like? So here's that whole equation with the energy solutions. And as you can see, what I have is the problem right here in front of me. Okay? So now when both nx is 1 and ny is 1, we have what's very analogous to our 1D particle in a box problem, which remember was just this, single hump, if you will, right? Well, now two-dimensionally, this becomes like a little hill, okay? So this is a contour plot, but if we wanted to look at this, at an actual somewhat, two-dimensional representation, it looks like this little hill, right? This little hump, okay? Very cool. So now what happens if we make nx2 but ny1? Okay, so now we get these two humps, and as it turns out, one will be positive and the other will be negative, just like a sine wave, a positive lobe and a negative lobe, which is established by this picture right here, okay? But if I change the x to 1, but now I make the y 2, it just rotates that same solution, but by 90 degrees. Oops, there it was a little slow, okay? So now that's that picture that we've got here, okay? But now what if both of them are 2? So then we get these 4 quadrants, all right? And so, on the contour map, if we wanted to look at that, and I've just got psi squared that I'm showing you here. So we see both are positive values. If it was just psi, we'd see a positive and a negative, right? So now if I go to the case where they're both 2 and 2, we can see these 4 lobes, okay? And so we're establishing, once again, kind of the same notion as the one-dimensional particle in a box, right? If I go back to the 1-in-1 case, what this is now showing is, our particle that was confined, like to this little plane on the bottom, you can see for the 1-in-1 level, the most likely place is predicted to be right in the middle of the box, okay? And so in other words, all of those momentum states would be converging to placing that particle right there in the middle. Now what's cool is as we go up to these various levels, this is definitely where we start to see this kind of funky quantization occurring, where now the particles become confined to various quadrants. Right, if I keep going up by the square, we'll get more and more of those quadrants. But just as we established with the correspondence principle, right, as we go up to higher and higher of those levels, it'll really just show us the particle can exist anywhere on the plane as we achieve really, really large n values. Okay? So what happens if we were to keep going with this and we established this as psi of x, y, z? So could we establish psi of x, y, z? And as it turns out, we could, and it would be very straightforward through the exact same separation of variables. And I'm just going to write that result down directly. Okay? So that's going to go as the square root of 8, and the reason why it's 8 is because it's root 2, root 2, root 2, 3 of them. And now that's Lx, Ly, Lz, right? We're still going to have this sign of nx pi x over Lx. We're still going to have this sign of ny pi y Ly. But then, as you might imagine, for 3 dimensions, now we're going to get an nz pi z over Lz. And I'm not going to write down the energy solution, right, for the 3-dimension, but it'll look exactly the same as this 2-dimension, where there'll be an n squared over L squared plus ny squared over Ly squared plus nz squared over Lz squared, but still times our 0.h squared over 8m. Okay? And what I'll also say, it's at this point where we're going to quickly transition away from this XYZ scheme, because it's not so practical for us to view this 3-dimensional representation with this XYZ scheme. As it turns out, what's going to be more useful for us is to switch this over to the R theta phi. Okay? That's where we're going with this thing. All right? And so the last thing, oh my gosh, look at that. I had it already expanded into the 3 dimensions, so I didn't have to write that crappy equation that I just did. So there that is. So what did I have here? So I want to talk about also what this model predicts is the concept of degeneracy. Okay, so degenerate states are different wave functions. So they're wave functions that describe different states, but those states have the same energy. Okay, so for example, so the way that this notation is written, those 2 numbers correspond to the different n numbers. So for example, if I wrote psi 1, 2, I would have root 2L, okay, times psi of 1 pi x over L times sine of 2 pi x over L. All right? And if we were to look at the energy solution for that, remember, that comes from right here, okay? Just adding up those 2 numbers, right? If n is 1, then it's 1 squared over L squared. And if ny is 2, then that becomes, 4 over Ly squared, okay? And also, if we assumed that the length of the x in dimension is the same, all right, then this energy level 1, 2 for the state psi 1, 2 becomes 5h squared over 8ml squared. Well, what if we switched the order of those n's? And not even really switching the order of the n's, but just literally making them different numbers, like a different state. So these are 2 different states right here. So psi 1, 2, psi 2, 1 are technically different states. However, if we look at the energy result for E21, it's the same as E12. So this is going to establish this notion that we call degeneracy. And this is going to come back later on when we're establishing even more physical reality, such as the atomic orbitals. As it turns out, degeneracy is really important in discussing the atomic orbitals. And what I also kind of wanted to show you, this figure right here, when you look at the psi 1, 2 and the psi 2, 1 state, the 2 states are related to each other by 90 degrees. So we could say they're orthogonal, right? They're different states. And I mean, literally, we can see they're orthogonal, right, by making them go 90 degrees. But they still have the same energy solution, which is very cool. So that makes them degenerate states, okay? Yes, I already, talked about that, expanding it into 3 dimensions. And the last thing that I want to talk about with this particle in the box problem, which is really, really cool, a cool application, is the particle on a sphere model. So as we established, right, we can easily convert this into 3 dimensions, psi x, y, z. Okay. What will become more practical will be to expand this into psi r, theta, and phi. All right. And when you do that, so this del squared right here, that's what this thing is. That's showing me the 3-dimensional second derivative operator. Okay. If I expand this into r, theta, and phi, then instead of doing a particle in a box, I can describe a particle in a sphere, which is a lot more physically practical. So for example, suppose now I'm just drawing you my x, y, z coordinate system, okay? And so let's establish the boundary conditions. So maybe instead of, putting my particle in a box or in a 2-dimensional plane, or even forcing my particle to be, in a cube, particle in a cube, what if I said the particle has to exist somewhere in this sphere? Well, we can do that problem. It's really nasty because you have to make this coordinate transformation. However, the solution is nearly identical to our particle in a box solution, which is really cool. So again, our particle in the box solution, let's find one written simply here. Where did it go? Yes, n squared h squared over 8ml squared. Particle in a box. Well, you can do this substitution of variables for the 3 dimensions. You can transfer it to an r theta phi coordinate system, which is going to be challenging, and that's where we're going to start working towards next. But you still get a solution that's practically identical to our particle in a box solution, which is really cool. So, and this also establishes the same situation with n. N equals 1, 2, 3, 4, etc. Okay. Me, that's the mass of an electron. Okay. Mass of electron. And now this r is the radius of the sphere. Okay? And so we established the same thing here. All right? As, what I want you to call, what we established, as the box gets bigger, right? And now it doesn't matter at this point if it's a box or a sphere or a plane. It's the same physical implication. Okay? So as our sphere gets bigger, the energy has to get smaller, right? So if the energy is getting smaller, that means the wave that fits in this box or sphere or whatever, right? I'll go back to just the very simple 1D result here, right? Our simple 1D result shows you, right, as I make this box bigger, look, the wavelength is getting bigger. As I make the box smaller, the wavelength is getting smaller. So what does that mean for physical reality? Well, look, here are some quantum dots that somebody synthesized. So quantum dots are, it's a fancy word for a nanoparticle. And these are nanoparticles made up of cadmium and selenium, okay? And here are the, I believe these are the diameters of the particles, okay? And you notice there's a really cool trend. The very small particles appear blue to our eyes. The bigger particles appear red to our eyes. And as the particles get bigger, they push more into the red end of the spectrum. Or in other words, as the particles get smaller, they push more into the blue end of the spectrum. This is a direct result of the particle in a box or particle in a sphere phenomenon. So in other words, in these nanoparticles, right, these nanoparticles are these little spheres. And they have electrons. They have a lot of electrons in them, but all the same, they have an electron or a mole of electrons in them, okay? Those electrons have energy level n squared h squared over 8 me r squared. And so as these nanoparticles, as they actually get bigger, they become more red. As they actually get smaller, they become more blue, which is really, really cool. And this is a really cool phenomenon that you all can do in the lab on free rotation experiment, those of you that are lab students. There's an experiment that we can do synthesizing gold nanoparticles. And we can synthesize different sizes of them and establish through their spectrum, we can figure out what size they are just based on where they absorb, right? As they absorb out to the more red end of the spectrum, we know they're bigger. As they absorb down to the blue end of the spectrum, they're more blue, okay? So this particle in a sphere, particle in a box problem, it has real physical observables, right? I'm always saying that word, physical observables. This is a physical observable of the particle in a box problem. The observation that color of an object changes with its size, okay, which is very cool. Okay, so really quick review of the learning goals thus far, because I know those are two pretty heavy lectures. So be familiar with the general wave function solution to the 1D time-independent Schrodinger equation, a sine x, b cosine x, right? So know where that comes from. That's mostly from chapter 7 stuff, okay? So be able to convert the general wave function solution for the 1D particle in a box problem to this specific wave function by applying the boundary conditions. So be able to follow that process where I started with this psi of x equals a sine kx plus b cosine kx, and using the boundary conditions of the particle in a box problem, we established that that wave function really is, root 2 over L sine n pi x over L, right? So be able to do that. So understand where principal quantum number n comes from and what it means. So principal quantum number n comes from the boundary condition, okay? And it's what establishes quantized solutions for energy, okay? So be familiar with wave-particle duality implications of the particle in the box. So that kind of comes from talking about how the expectation value of momentum is 0 for the particle in the box. And that's because there are, it's a superposition of left-moving and right-moving particles establishing its position right in the middle of the box. So be familiar with energy levels. So that's kind of related to that level n that we were just talking about, okay? How those establish as, they go up by the square. So be familiar with the separation of variables technique. So we went through that today in this lecture. The concept of degeneracy. So I just talked about that. Beautiful. And then understand physical manifestations of particle in a box and what it means for quantum dots or other real-world applications. So that's kind of what I was just talking about, where with this particle in a box problem, we can actually observe the particle in a box at play by changes in the absorption spectrum of this material, all right? And so I'm just going to do one more lecture for this little subset in Chapter 8 on translations, which will describe the tunneling phenomenon. Okay, folks, I'll see you later.